Okay guys, last lesson I introduced to you the chain rule. I just want to continue that today with a bit of practice using a different variety of resource. First thing I would like you to do is some basic differentiation work. You've seen this task before. Bring on the maths. All you need to do is match the functions with their derivatives. Okay, I'll give you 3 minutes. Off you go.
Match the functions with the thing. Is that not up there?
It's
Or
not
am I
up
just
there,
being
no.
blind?
So some, you're saying that some of them won't have a matching
Some of them
buddy.
don't have them.
Yeah.
Right.
Some of the functions slightly harder than others. Think about what you might want to do with the top right function, function in brackets. Can you differentiate that straight away?
Root x isn't up there either, is it?
Root x differentiates to
A half x to the minus a half.
y.
Because root x is the same as x to the power of a half.
Good.
And then you bring the half down and take 1 from it.
And that gives you which?
Minus a half. So half x to the minus a half.
Excellent.
There's only half x to the half up there.
Okay. Okay, let's go through the answers then. Start with the top left. Y equals x squared. Matt,
2x.
is its derivative. Excellent. Bryony, x cubed.
It's not up there.
It's not up there. What would its derivative be?
3x to the square.
3x squared. Excellent. Daniel, y equals 3x.
Goes to 3.
Excellent. Just becomes a constant. Alex, what would you do with the top right one in brackets?
Expand out the brackets.
That leaves 2 left over. Volunteer to come to the board to show us how 1 over x differentiates to negative 1 over x squared.
So 1 over x, same as x to the minus 1. Then to differentiate it, you bring the minus 1 in front of the x, and then drop the power by 2. It's going to be the same as minus 1 over x squared.
How would you write that formally using function notation? Okay, excellent, yeah. So, if we match them up on the board, you know the game. Just got an anagram of letters. The word. Andy tends to be quite good at this.
Derivative.
It is derivative. Excellent. Yes. If we just gather around the Velcro board at the back. Last lesson, we ended up with me teaching you the chain rule and going through a couple of worked examples. Up on the Velcro board here is 2 such examples. What I want you to do is unjumble them and put them perfectly. Give me a perfect work solution. Okay. Any questions? Off you go. Work as a group. Work as a group.
Did you say there was 2? Right. That's the question. So that would be 1, that's 2. And then I suppose you state 1. So
Y equals 2x plus 3.
yeah, and then where's the u? So then you do that.
As you're working through this, think about why we use the chain rule. Okay.
'Cause it's
For what
easier.
type of functions
Composite function.
What
It's easier than
benefits
using binomial
the
expansion.
chain rule has.
Do we want that one first or the other one first?
Wouldn't really
Where's
be
the
that, would it? You'll have it, which is that.
Yeah, and then that goes to that.
And that.
So that is that the first one, right?
And then
Actually, we want this up here Because it's at the.
And then
finding
dy
the
by
peak.
dx you put 0,
Yeah.
so that'll be at the very bottom.
Yeah.
So it's 3
Right, right.
equals 54.
There we go.
So
That's
for
that one.
So possibly one solution complete, possibly. There's
Oh,
a
yeah,
second
because
one
it could
also.
be-
So yeah. Yeah, just start on that one then.
Right.
Go a bit louder, Dan.
So we've got dy du equals
du by
dx
dx.
would be the 3.
And that's the formula to use.
Yeah.
So you substitute
And
it
then
in.
you've got dy by dx equals that.
It's 3.
Think about the last one you've put down there.
Oh yeah.
That's the same as this one up here, isn't it?
So it's going to be 2 times 3 for that,
That would be 6.
which is 6.
Yeah. So these have got to go on here. These have got to be from this one because they're the only ones with the same function in.
Okay, so where are you going to put that one? Where logically?
That
Yeah,
one would go in there.
Yeah, above the peak.
Wouldn't it?
Spot on.
Oh yeah, because that goes in there. Ah, so
Yeah,
And-
y equals.
And that one doesn't go anywhere.
this one doesn't go anywhere. Right, so it's
That one.
yeah, and that one goes there. Oh no,
Other way.
there, like that.
Alright.
Excellent. So those are the workings we're looking for. Explain, Matt, find the gradient of the curve y equals 2x plus 3 to the power of 3 at point 0, 1. What have you done?
We started off by making that formula there into u, which would be that, and we would then substitute u into the y equation, which would then equal u cubed.
Excellent. Why do you start off by doing that? What's the whole essence behind the chain rule? Why do we use it?
It's easier than expanding 2x plus 3 cubed.
Excellent. What methods are there to expand that function?
Binomial expansion.
You could use a binomial theorem or,
Do we know
going back to GCSE,
Oil.
FOIL, yeah? What type of function do we use chain rule for?
composite function?
Composite functions. Explain. What do you mean by a composite function?
Where it's got a function inside another function.
Excellent.
What do you mean by stated?
What does the chain rule say in terms of your composite function? How does it work? Go through the procedure to me. Then you've worked out dy by du by dx, multiplied them to get your derivative, your gradient function. Explain the last two steps for me. Can anyone help her?
Because it's at the point 0, 1, so you've got to put 0, 1 into the equation.
Yes. Let me just go through the second example with you to explain what gradients and derivatives are all about. Derivatives are all about rates of change of one variable with respect to another variable. Going through this particular example, this expression here, dy du, is basically saying that y is changing twice as fast as u is. This expression here is saying that u is changing 3 times as fast as x. And overall, therefore, y is changing 6 times as fast as x, which makes sense, doesn't it?
Yep.
Yeah? Okay. It's going to be an assessment task. The assessment task. There are 20 assessments on the chain rule in Maths and Net, quite a few. Maths, pick me a number between 1 and 20. 3? Okay, so Matt's chosen the questions. We've got 3 questions in total. I only want you to answer the top 2 because as yet we haven't looked into differentiating any of the trig functions. Up here, I've given you the answers, okay? What dy dx is. What I want you to do is produce me perfect worked solutions to get from the function to their corresponding derivatives. I'll give you 3 minutes on each, 6 minutes in total.
Is that e to the 3x to the 4? Up there.
That is,
E
yes,
to the 3x
e
to the 4.
to the 3x to the power 4 plus 5.
You are differentiating du by dx, okay, because the function's in terms of u.
So,
Multiply them together gives you that final answer.
so
Excellent.
that's, like that.
And that'd be spot on.
Use that.
Excellent.
Right.
On to the second one.
Okay. If y equals e to the x, what happens when you differentiate it? No, no. When you rearrange it, ln and e are inverses, yes? When we differentiate an exponential function, e to the x, it stays the same. Excellent.
I just wrote up the formula, what we've got to solve here. Which made y equals to e to the power of u, and u equals 3x to the power of 4 plus 5.
Excellent. So Matt's identified the components of the composite. What's next?
Dy over du. So that equals e to u.
Excellent. The exponential function stays the same when you differentiate it.
And du by dx equals 12x cubed. So I've differentiated u.
Excellent.
And then dy equals 12x cubed e to the power of u.
Excellent. So the chain rule says to find the product of those two derivatives.
And that then equals 12x cubed e and then 3x to the power of 4 plus 5.
Perfect. Okay. Well done, Matt. In this space here, dy dx equals dy du du dx. Okay. On each bit of card, there is a function. What I want you to do is calculate the gradient of each of these functions at x equals 1. The answers will be on a different piece of card, okay? The 10 cards loop around, and the first to finish all 10 cards will receive any treasure that I might have to give away. In this case, sweets. One of the hardest things with the chain rule is to actually identify the individual components which make up the composite function. Be careful that you choose the right components.
I've done that right.
You've identified u to the 4 and 3x plus 2. You've differentiated, correct?
Yeah.
Multiplied them together. The only issue is
That's
the,
a 4, not a 2. Oh, it's a 3.
the power you
That's
haven't
what it is
brought
then.
down.
Oh yeah.
Got to identify the components to begin with. So if y equals 2e to the u, which of these expressions is u? Excellent. So put u equals in front of it. Now you've set up the problem, it's very easy to continue it. You are differentiating y
then I put it back into the thing.
You could put it back in, but you've actually, at the moment you haven't actually applied the chain rule. You've found the individual derivatives.
Well, that's what I did last time. I put them back into the thing.
After you did what?
Find dy dx.
Good. So
That's
find,
what I did to you.
you found the udx.
So now actually, okay.
What is actually the chain rule?
dy
dydx is equal to
dy
derivatives. You've got to times them together.
and
Perfect.
then you put it back in.
Now you put the u back in. Excellent. You're raising it to an even power, which will make it positive. Now, why is that an issue? It's not 5, it's 7. It's your writing.
Oh, it's -2.
Okay. That should have an effect.
-1. That's where I'm wrong.
-1.
Oh no, yeah, it's still 1.
Yeah. Therefore, the brackets become
-0.
so.
It's 0.
Excellent.
That's my formula, and it'll give me.
Okay. What I want you to do is decide which of these functions can be differentiated using the chain rule. Okay. Just a reminder, why do we use the chain rule?
Differentiate composite functions.
There's two answers there, Alex.
Differentiate composite functions.
To differentiate composite functions, and Andy, what did you say?
Easier than expanding.
If the function was one which included brackets, yes, it'd be easier than expanding. Well done. Okay, so we've got a trig function up here, sine 2x. Is that a composite function?
Yeah.
Yeah.
Explain.
So if it would be y equals sine of 2x, so it would be y equals u. Oh, could it be y equals u and then u equals 2x? Sine u and then u equals 2x.
Excellent. Well changed there. Yes, those are your two components, sine u and u equals 2x.
And the only function in there is tan x.
Yes, the only function there is tan x. Ln x squared?
Yeah.
Yeah.
It is. There's no other way of defining ln x. Sine x. So that's your u. And what's the
1 over u?
1 over u, excellent, is the function that you substitute sine x into. We'll do one more.
1 over cos.
Excellent. Sec x is 1 over cos x.
So u will be cos x.
U will be cos x, the function you substitute in,
Y is 1 over cos.
and y is 1 over u. Excellent. Okay, well done, guys. Next lesson, we will take the differentiation a bit further. We've looked at the chain rule here, okay, which differentiates composite functions. Next lesson, we will look at the product rule, which involves differentiating two functions being multiplied by each other. An example of that would be x cos x. Okay, thank you.